Shall we move on? Okay, I have a problem to compute the x bar. So now tell me, what is the true mean of throwing a die? True mean is what? You know the probabilities here. What is the true mean of throwing a die? So that is why I have given this example. In a roulette in US casino is where money is, right. So if I know the answers, ground truth, I will get better outcomes, and if I know the ground reality, mean value, you think I can earn more? US casinos are never designed that way. Okay. So look at this, in a roulette in a US casino, a $1 bet on even wins $1 if the ball falls on an even number. Same for odd or red or black. Okay. What is the odds of winning this bet? So what is it? If I bet on a even number, if I bet $1 on an even number, wins you $1. That is like your output doubles, your investment or your bet is double. So you put $1, you get how much? $2 if you win, that is like 100%, right. That is what usually in casinos is, 100% is even less, you get multiple times. Okay. If the ball falls on an even number, and similarly it is same for odds or red or black. Now tell me, what is the mean and what is the variance, and what is strange about this? What is the probability of winning $1? What is the probability of winning $1 in a roulette wheel? How do you calculate? What is the probability here? 2, 4, 6, 8 out of 10. So what is it? Probability is 4 by 10, 4 by 9, right, 1 to 9. I do not know whether 0 exists. So 1 to 9, I am also not aware of this roulette wheel business on 0, 1 to 9. So 1 to 9, it is 4 out of 9. So your probability is less than 50%, that is like 47%, and lose is 52%. Usually all the games are designed in such a way that probability of win will be lower than probability of win will be less than probability of lose, that is when they can make money. Okay. Now what is the mean value? So $1 into 0.47 minus $1 into 0.52, that means the mean value itself is slightly lower than 0, the mean is tweaked towards you losing, okay, not you winning, the mean is slightly tweaked towards you losing. But still, why do we play the game? Not just for money. If I know that I am going to lose, why will I play? That is not attracts so many people. Why do they call it a stance, and why not say, hey, it is always that fellow will win? Have you not seen lottery tickets? Still people buy and win. Somebody makes money, many people lose something, but someone makes big money, right. So why is it, why do still people play? The second fellow, variance, the variance is too large. It does not mean variance is 0. If variance is 0, I will just do not even enter the game. Why? Because anyway I am losing and I am sure I will lose, but here the variance is very large, right. Why do you say that throwing a die is actually a chance, is purely a chance, outcome is purely a chance. Mean value is 3.2 actually, if you compute it. What is the mean value of throwing a die? Can somebody tell me quickly? Compute and tell me. 3.2 is not the exact answer. You solve. Unless you do it yourself, you will never learn. What is the mean value in throwing a die? Tell me. What is the answer? How do you compute? Somebody, how do you compute? Anybody from there? How do you compute the mean value in throwing a die? What is the true mean? 4 of you there, nobody will look at me. How do you compute the true mean? That is how you have to do. How do you compute? What is the true mean? Expectation of x is equals to summation p of x times x. So what are the x values? in a throwing a die, what are the x values? 1 to 6. What is the probability? 1 by 6. So how do you compute the answer? 1 by 6 into 1 plus 1 by 6 into 2 plus 1 by 6 into 3 plus 4 plus 5 plus 6, that is all. What do you get? 3.5. Now the mean is 3.5. You all agree how to get it, you all know, remember, no, right? So 3.5. What is the variance? What is the variance? How do you compute the variance? Mean is 3.5. So what do we do? Expectation of x minus mu the whole square. So 1 minus 3.5 the whole square plus 2 minus 3.5 the whole square, 3 minus, so it will be a, will it be 0? Will it be small or large? Will it be 1 or will it be 3? Variance. Before we do math, you know, we are all engineers, we are not mathematicians. We should know the outcome, we should predict the outcome. What will be the outcome? Will the variance be lower or larger? Why? That is why you cannot predict the outcome. It can be from 3.5 all the way to variance of 3, that means it can be anywhere between 0 to 6, that is what you can compute. What is the answer? 3.5 minus 2.9, what is it? 0.6 on one end, on the other end it is somewhere 6 point. So really you do not know where the outcome will be. That is why throwing of a die is purely a chance event. Not the mean is important, mean alone is not important, it is the spread also important. If your spread is small, that means what can you do? You can predict. If your spread is large, not possible to predict. Understand what I told you the other day also. What is the best predicted in terms of mean square error? Mean. If you do root mean square sum square error, it is going to be the mean value is the best predictor. Now in order for your prediction to be error to be less, what it should be? The true distribution should have a smaller variance. If the true distribution is large, then your estimates will be poor. You understand what I am saying? If your true distribution is large, variance is large, then it is very difficult to predict. That is what happens in throwing a die. Your true distribution, true variance is large, so you do not know what will even happen next time. But if the true variance is small, then you could predict better. Same thing. What is the mean? 0.5. Convert it into a random variable of 0 to 1 first. Head is 1, tail is 0. The mean is 0.5. Look at the variance. Half square into 0 minus 0.5 the whole square plus half square into 1 minus 1 the whole square. You will have the same number. Variance will be high. Okay. Same goes for tossing of a coin or throwing of a die. If you computed half square 1 by 4 into 0.5 square plus 0, the other one is 1 minus 1 the 0. So it is not going to be less. And the mean itself is 0.5. So 0.5 minus 0.25 is 0.25, 0.5 plus 0.25 is 0.75. So you are saying anywhere between anything can happen next moment. Okay. So if the variance is large, you have a problem. Okay, it is very difficult to predict. So you want two things, you are focused on mean, but at the same time variance should be as little as possible for you to predict better. The true variance. Now let us get into some bit of population as well as definitions. Okay. So we all know what is a population, totality of observations, a sample, a subset of observations, and here is when I define a statistic. So far we have been calling it as a quantity, we will not anymore call it as a quantity. X bar or sample mean, sample variance, is any function of the sample. Observations in a sample is any function of a sample. What does it do? That tries to estimate the population quantity or population parameter. So, a statistic is always a function of sample, and the statistic usually tries to estimate the population parameter, and we have this. So, if in general I call theta hat, the hat stands for always an estimate. A theta hat is a statistic which is an unbiased estimator for the parameter theta. This is population parameter. So, a statistic theta hat is an unbiased estimator of the population parameter theta if expectation of theta hat equals to theta and variance of theta hat. So, this is unbiased, expectation of theta hat equals to theta or the difference is 0. So, I have already proved expectation of x bar equals to mu. So, x bar is an unbiased estimator of mu. Make sense? Clear? X bar is an unbiased estimator of mu. Okay. Now, how about sample variance? What is my sample variance? You all know what is population variance. What is the formula? How do I compute sample variance? We call it as S squared. Sample variance is nothing but S squared. It is given by 1 over n minus 1 times this is my sample variance, summation of x minus x bar the whole square divided by n minus 1. This is sample variance. Why n minus 1 and why not n? You all understand, right? 1 over n minus 1 summation x minus x bar the whole square is the formula for sample variance. And what is the definition? Usually we want the sample variance to tend to, sample variance should converge to, sample should converge to, statistic should converge to true estimator, right, true parameter. So, sample this should tend to population variance. So, can we prove that? Yes, I will let you do the this thing. I have shared the presentation already. Karthi, share. It's already been shared. So, go through it. This actually will tend to sample variance, will tend to population variance. This expectation of x squared equals to sigma squared, okay, for this formula only. If you put n, it will not work out. And there is also another logical answer for why n minus 1 and not n. The logical answer is very simple. Suppose I give you 10 values. So, there are let us say 1, 2, 4, 6, 8. What is the mean? 21 by 5. Okay. Suppose I give you these 4 numbers and I ask you a next question and then say x bar is for this sample is 21 by 5. Can you not guess the next number? Can you not even guess? Can you not exactly determine the next number? Why? Because this is nothing but summation of xi by n. Okay. You do not know one xi, but you know all the other x values. You can compute the unknown value, right. So, what it simply means is if you give me x bar is equal to like 1 degree of freedom. We call it as what is degree of freedom here? Degree of freedom is the total number of independent data points that can be used to estimate the statistic. Total number of independent data points that can be used to estimate the statistic. The statistic in this case is s squared and the total number of independent points is not n. Why? If I know n minus 1 data points and x bar which is used in the formulae, then you can estimate the nth data point and therefore you only have n minus 1 independent data points, and that is the reason why you divided with n minus 1. You understand what I am saying, right? See, you are in the formula for the variance already you are using x bar. So, how many independent data points are there actually? Only n minus 1. This n minus 1 independence of data points is also called as the n minus 1 degrees of freedom. So, you have only n minus 1 degrees of freedom, okay, and this n minus 1, that is why you divided with n minus 1 degrees of freedom, okay. You usually divide by the number of degrees of freedom, not the total number of data points, okay. This will also turn out to be the unbiased estimator. If you derive this, use this, it will also turn out to be the unbiased estimator. So, sample variance is an unbiased estimator of the population variance when this formula is used, when 1 over n minus 1. Of course, if n is really large, then n or n minus 1 it hardly makes a difference, okay, you do not really care. If n is like 10,000 or 100,000, how does one data point going to make a difference? Nothing. But if it is n is 10, another n minus 1 will make a difference, okay, clear. For small samples this will make a difference, for large samples you can neglect it. Make sense? Clear everyone? Okay, so welcome back. So, we have looked at probability distributions, I mean probability, the basic parameters of probability distribution like mean and variance, and we looked at how to do it from statistics and what is the relation between the estimate samples, the statistic and the population parameter, right. Now, what we will do is we will slightly delve more into probability distribution function, okay, and some of the commonly associated distribution functions. And one may wonder why is it that I have to do it. Remember, in some of the cases, not all real life examples you will know a probability distribution, but in some of the cases you will get to know the probability distribution by the nature of the experiment itself, and that is the reason why it is important for you to understand the some of the existing distributions. There are so many distributions out there, we will learn only a very handful of them which are important ones, which are most occurring in nature and which can be related to biomedical as well. And the other important thing that I established, that I seek to establish by doing this distribution studies is I want to know the statistic distribution of x bar. I want to know the distribution of x bar. Why? Suppose you have computed x bar, you know what is the, you do not know what is the true mean, you have sample mean, and sample mean is an estimate of population mean, right, x bar. Now, I want to not only give x bar as an estimate of mu and say, hey look, as n tends to infinity x bar tends to mu, nobody is going to accept that. Why? Because you can never do infinity samples. Suppose I have computed 10,000 x bar from 10,000 samples, and I can ask you a question, see how accurate is your x bar, how close is your x bar to true mean mu. Suppose if I take 1000 samples, you say can you give a number. Suppose you want to be more accurate, if I do 10,000 samples, will I be more accurate? How much will I be more accurate? These are the questions which one intend to answer, you understand. Now, true mean is not known, I am going to estimate true mean. So, in your case let us say antibodies, some x antibodies have developed or some x patients have got cured, the probability of cure is some x 0.8, okay. You seek to prove that your medicine in clinical trial works with a probability of 0.80% of time it works. Now, you are only going to take samples and your probability, you can compute probability of success, that is clearance by samples. So, now suppose it turns out to be 0.75, okay, it turns out to be 0.75 from your samples. What is your claim? Your claim is 80% of the time I want to make sure this works. Now, your claim is what? Now, your x bar is what? 0.75. Should I tell that this medicine is not working, or should I tell that this medicine is working? This trial is good or bad? 0.8 is my accuracy, I want 80%. Your success rate is 75% from a certain sample. Should I disregard the null hypothesis should I disregard the hypothesis that yours is working or not working? What should I do? Should I accept that it is working or should I reject that it is not working? What should I do? How do I go about it? You understand the question? You wanted to prove 80% of time it is working. I stated what is the null hypothesis, then you are saying that it is not working. The alternate hypothesis is what? It is working 80%. You collected samples, what did you get? Your x bar to be 75%. Now tell me, based on this what can you conclude? Can you even conclude, or based on that what can you conclude? Not working. Why? Just because it is 75. So suppose I give you 85, you will estimate that it is working. Why? I told you mean alone is not going to be important. What is going to be important along with mean? Variance, right? And that means I should ask a question, in fact the question itself is wrong. I should ask a question not 80% or not alone 75%. How much percentage you are confident that your medicine is working 80% of the times? Are you confident 95%? Are you confident 90%? Maybe with sample 75%, 75 x bar, I may be confident 60%. Right? So the question itself should be thought through. You cannot simply say it will work or it will not work. Why? Basically because it is a random process. After all, it is a random experiment. The outcomes cannot be sure at all. So then you can only be confident certain percentage. You can never be 100% sure. 100% sure, the answer is straightforward, do n tends to infinity. That is not possible. So now when you do not have n tend to infinity, the next question is how much percentage I can be confident about. That will require not just distribution of, you will require the distribution of x bar. Suppose x bar as I said is 75 and then suppose x bar turned out to be 85 and then both the sides the variance is 50, what will happen? So x bar plus or minus mu sigma plus or minus 1 sigma is how much? 85 plus or minus 50, that thing is next value could be anywhere between everything. Basically even if I put 20 it is bad, it could be 60 and 100. Now if I say mu my variance is 1, then x bar plus or mu is 85, 84 to 86, which is excellent, right. So I need to know the distribution of x bar. So what we seek is, going forward is we will learn a few distributions which are very commonly occurring, and towards the end we will seek to learn the distribution of x bar, not x bar, okay. That is generic. X will depend upon experiments, but x bar will become generic. Irrespective of x, we will define the distribution of x bar, okay, with some conditions on x of course. So that is the agenda. So we will start with basic distributions which are quite common. The first one is binomial distribution. These are some things which you would have learned in your undergrad, okay. I am going to quickly rush through it, I will stop when and wherever important, but otherwise these are things you should have known earlier. So a binomial distribution, what is the characteristics? Give me an example, what are the characteristics? Give me an example of a binomial distribution. Sequence of tossing of a coin, not just tossing of a coin, keep that in mind, it is a sequence of tossing of a coin. So each trial is called as a Bernoulli trial. Each trial is called a Bernoulli trial, and there are n identical trials and there are only two outcomes, success or failure. So P and 1 minus P is my success and failure, and the key factor is trials are independent. So what does it mean? If you see a Bernoulli binomial distribution, what do? Do you go ahead and try to predict, or do you run away? Basically, if it is a binomial distribution, you say thank you, that is it. Why? All trials are independent. What is there to get, this trial and next trial, they are not even related. So you do not work with a binomial distribution. Okay. Whenever binomial distribution you see, okay, this is like the something which you cannot model. Okay. In a related note, on a related note, we have what is known as IID sequence. What is the IID? Anybody? Have you heard of this term IID? IID? See, IID sequence is also called as independent and identically distributed sequence. The throwing of a die or tossing of a coin is an IID sequence. Each tile is independent and they are all coming from the same distribution, which is the binomial distribution. Okay. And if I say, the moment I say IID sequence, you should know that you cannot model it, period. You do not have anything to talk about it. Okay. But in reality, there are very little IID sequences. I told you, like last class also we discussed, birth and death, all of them have relationships, history, past, right. So IID sequence is a rare sequence, but the moment you see IID, you know that it is not good to look at it even, it is not good to, you cannot model it basically. And binomial distribution is a classic example of IID distribution. Okay. Each trial is independent and there are n identical trials, there are only 2 outcomes, success or failure, and your probability distribution can be given by what? NCX p power NCR p power r, NCX p power x, q power n minus x. This is your simple probability distribution function. And I said probability distributions can be easily written for only easier cases. In real life situations, deriving probability distribution is not possible. It is not at least easy, easy. So this is your binomial distributions. Okay, I have given some examples, I would like you to go through it. These are things which you should be doing. And what is the mean in binomial distribution is NP, standard deviation is square root of NPQ and variance is NPQ. Okay. You can take expectation of x minus mu x and derive it. Okay. You can take what is mean summation x into f of x, you can compute and this is what you will get. Okay. Clear? So this is my binomial distribution. The next one we are going to look at is Poisson distribution. Okay. This is also everybody have heard about Poisson. What is this distribution for? Usually characterizes what kind of things? Independent events is characterized by binomial. What kind of events does Poisson distribution characterize? Periodicity, no? Huh? Uncertain, everything is uncertain, the random experiment itself is uncertain, outcomes are uncertain. N is large, okay, so then N is large, good, go on. What kind of events? That is when you learn, you do not mug up, you do not characterize based on whatever you think. So binomial distribution is for independent events. What is Poisson distributions for? Rare events. Binomial distribution is a discrete distribution. Poisson is also a kind of discrete in the sense it is usually for rare events. So if I ask you the number of accidents happening in IIT Madras Road from in the Bonn Avenue or in Adayar Avenue or let us say in Alumni Avenue, it is going to be at least in Adayar Avenue it is going to be a Poisson distribution. In Alumni Avenue the students are very good that the accidents are common, right, with a mobile phone, and it is not just the students, it is everybody included. So I do not know about Alumni Avenue which is our avenue, the main avenue, but in Adayar Avenue which is a very small road, probability of accident is very small. So, this Poisson distribution is usually used for characterizing rare events. What is it? This is usually used for characterizing rare events like earthquakes. 2 earthquakes happening in a span of 1 hour, probability is actually 0, right. So, 1 earthquake happening within a month in Tamil Nadu, it is very rare. God forbid it should not happen. I did not even want to bring this example, somehow it came to my mouth, okay. But yes, right, it is a rare event. So, it evaluates the probability of number of occurrences out of many opportunities in a small period. So, look at usually small. So, n is large, p is small, okay. So, you take a binomial distribution, make n very large and p very small, then it will become a Poisson distribution, and there is no probability of 2 events at all. One success only is rare, the probability value for success is so low that there is no 2 events going to happen even, okay. So, probability of 2 things happening, rare events happening is 0. So, here we are talking about probability of occurrence of one rare event over a large n, okay. So, that is where this idea comes in, n large, p small, right. This is what you would have learned in undergrad, immediately make n large and p small you will get, but the phenomena, the thought process is this, you are looking at rare events over a longer period of time, got it. So, that is when you make n large and p is very small. So, you get what is known as NP becomes lambda, okay. So, the distribution is lambda power x e power minus lambda by x factorial. See, I would have derived this Poisson distribution if it was important, okay. I have not derived, actually we could, there is a neat derivation of how to get Poisson distribution from binomial distribution. Does anybody want to volunteer? Somebody who does binomial can be derived from binomial distribution when n tends to large and p tends to very small value, clear. So, I have given an example here for you to look at, okay. So far we have looked at discrete distributions, of course there are several other distributions of importance like geometric distribution, okay. Poisson, binomial, geometric, there are so many distributions, I am not going to go through all of that, it is not of importance, especially as biomedical engineers. When I looked at the syllabus, even I was wondering why the hell you should look so many distributions, you may never use it also. You need to understand the concept of distribution and a few important distributions. So, those are things I am chopping it off, okay. I do not want you to teach Weibull distributions or geometric distributions and so on. So, there are chi-square, so there are so many distributions, we will learn only the important ones, okay. Now, coming back to discrete distributions, we learned 2, both binomial and Poisson are distribute. In fact, the other important distributions like geometric distributions can also be derived from binomial distribution, okay. So, that is why those 2 are important, and when it comes to continuous probability distribution. So, so far we have looked at discrete, we are now going to look at continuous probability distribution. The continuous probability distribution, you do not even talk about no longer you will talk about a event as a point, it will be a region, interval, right. That is what I said, you are only talking about a interval. So, instead of probability of x as a one value, you are going to talk about probability of x taking on in a or happening within a interval. So, that is what probability of x lying between a and b, okay. So, like this curve you are talking about an event a which lies between these 2 points, the region, the interval between these 2 points. So, probability of a less than x less than b is mathematically equal to probability of a less than or equals to x less than or equals to b is equals to probability of a less than x less than or equals to, all are same because probability of a single point is 0. So, all these are the same, okay. You are only looking for a probability within a region, one point does not even matter, but the irony is at the end you will get only one point as the outcome, okay, like throwing a dot the other day we did. So now in continuous distributions we will worry about only two distributions, which is uniform distribution and Gaussian distribution. Okay. So first we look at uniform distribution. Uniform distribution, as we know, what is it? All points are equally likely. And why is it important? Why is learning about uniform distribution important? When I do not know anything about the happening, you always start with the assumption of uniform distribution. Let us say you do not know anything about your vehicle, okay. What is the probability of failure of an engine? Is the same as probability of failure of a horn, right, because you do not know anything about the vehicle. Assume if you know about anything about the vehicle, then your things will change. Engine will not fail so often like your horn or your speedometer. Most of the vehicles speedometer, is it working? Will it work like an engine for 10 years guaranteed? Especially the older vehicles, speedometer, at least in my vehicle I have never seen speedometer work even, okay, always 0 km/h, which is good, okay, I reach the destination, but engine has to work for me to move from one place to another, right. So probabilities, that is where things are different weightages, but when you do not know anything, then you start with an assumption that it is uniformly distribution. This is the safest bet. Without any prior knowledge, this is the safest bet. So all outcomes are equally likely. That is what results in a uniform distribution, okay. You can have both continuous as well as discrete uniform distribution. So that is why I did not specifically do the uniform distribution can be continuous or discrete. All outcomes are in other words x bar is based on this assumption, right. All outcomes are equally likely, all samples are independent and equally likely, that is why I do not give weightages, okay. So that is when it is commonly used x bar blindly. Why? You do not know anything about the process, still x bar is a good estimate. Why? I have assumed everything is likely, but the moment you know something better, x bar is not the best estimate, you understand. So suppose if I say temperature, I have taken reading from a thermometer and a gun and your x bar is this, you will have doubts. No, x bar is not a good estimate, you have to weigh it with the importance of the sensor, right. So you have to understand when x bar is important and when x bar is not important, when you have to use weighted x bars, okay. So uniform distribution, the assumption is all outcomes are equally likely and the distribution is simple, okay. For two values probability of A less than B, it is B minus A divided by the whole range D minus C. Everything is equally likely, right. So x can take on any values between C and D with equal probability 1 over D minus C, which is the overall range. This is the range, this is the range we are interested in. So all points are equally likely, so the probability distribution is simply by 1 over D minus C, that is it, okay. And mean value is the midpoint, all are equally likely. Now you see mu is exactly like x bar, midpoint, because there is no, all are equally likely, so it is C plus D by 2. So that is when x bar will have meaning with uniform distribution, okay. And standard deviation you can derive it, it is D minus C by square root of 12. Clear? Why uniform distribution? Any questions? So far so good, shall we move on? So I have given an example as well, you can do it. So before we go to the next distribution, should I give you a small example that you want to do? You want to do that? Okay. So slightly thought provoking, because the exams, when are your exams? Quiz 1. is not very far away, that is why I am taking classes, I am covering up things, meaning I do not want to miss even a single class. Huh? That week of 17th 18th, okay. So I do not want to have, typically I do not want to have class that week, meaning at least 2 classes I will give you free. So that week Tuesday Wednesday I will give you an off, so that you can prepare and you can prepare for other exams as well, okay. But before that I will cover everything, that is why I am trying to have special classes, okay, extra hours. So given that exam is also coming quite, so let us take, you know, let us take there are 4 buses which carry IIT students for placements, okay, and bus 1 has 60, bus 2 had 50, bus 3 is about 75 and bus 4 is about 25, okay. Let us make it bus 240. So total 200 students, okay. Now define 2 random variables, let x be a random variable which indicates the student, which denotes the student belonging to a particular bus if the driver is chosen random. So what do I mean by x? 4 drivers are there, I choose a driver at random and x denotes the students, x be a random variable which denotes the students belonging to a particular bus if the driver is chosen randomly, okay. Out of 4 drivers I choose 1 driver randomly, okay, and then I look at what is the bus, what is the strength of the bus, number of students in the bus. And the other case y be a random variable which denotes the students belonging to a particular bus, which denotes the total number of students, let us have it even explicit, which denotes the total number of students belonging to a particular bus if a student is chosen randomly. Okay, you understand the question? So in one case driver is chosen randomly and you look at the number of students in the bus. In another case student is chosen randomly and you look at the number of students in that particular bus, okay. Now my question is following: compute which one is greater, expectation of x or expectation of y. Totally 200 students, 4 buses, you pick up a bus, you pick up a driver randomly and look at the number of students in that particular bus, that is x. Totally 200 students, again you pick up randomly a student and look for the number of students in that particular bus, that is y. Now tell me what is expectation of x and expectation of y, how will you even go about doing it? questions will be of this fashion, okay. Do not expect questions to be of whatever we discuss in the class, like like simple what is expectation of, no derivations, whatever derivations I have derived that will not appear in the exam, you know that very well. So this is, let us say, one of the questions. At least quiz 1 will be slightly tougher than this, but let us say to begin with, how do you approach this problem? Somebody, how do you compute expectation of x? How do you compute expectation of x? X into f of x, how do you compute it? Nobody wants to volunteer?
Maybe in the first case we can take as like we are choosing one bus driver out of 4, then 1 by 4. For each bus we will take it separately, like for bus 1 the number of students is 60 divided by total number of students, plus for 1 by 4 into for bus 2, and this goes on till bus 4.
Yes, I have written it there. That is what expectation of x is. Not very difficult, if you start putting your head, it is not very difficult, okay. What is expectation of y then? Good, 60 by 200 plus into which one will be greater? Which one will be greater? Do not even compute, we are engineers. X is greater or y is greater? X is greater or y is greater? X is greater. Give logical answers, why x or y is greater?
Because number of students are there, first we are considering the number of students, so the number of students are more.
No, in the first case also it is number of students only, right?
They are only in first case is number of bus driver plus number of students.
The second, no, the weightage is different, that is all, the weights are only different, right. So how do you say y is greater than x? It should be based on weightage. Why is it? Both are the weightages are different, the x values are the same, weights are different. Why is y greater than x? Do not compute, without computing tell me.
First case weightage is 0.25 for all.
First case 4 drivers, if you choose randomly all are equally likely, but suppose you go to a country and pick up the number of immigrants from various countries, who will be large? Let us go to US, let us go to Texas, you know Texas, right, US, go to Texas and say the number of immigrants, you pick up an immigrant, how likely is that immigrant from India? Immigrant from India, Texas, immigrant, how likely is it to be Indian? Very high. Texas has Kanjipuram silks showroom, okay. Texas has all South Indian dishes whatever you want, okay. In fact it is much better than here sometimes, okay. So the moment you pick up an immigrant, it is more likely that it is going to be Indian. Why? There are more Indian immigrants in Texas. Similarly, bus 3 has more number of people, it is most likely that you will pick bus 3. Look at the weightage of bus 3, 75 by 100, whereas look at the weightage of bus 4, 25 by 100. So it is most likely to pick a student who belongs to bus 3 compared to bus 4, whereas in your x all of them are equally weighed. So naturally y will be having more weightage compared to, y will be greater than, expectation of y will be greater than expectation of y, because in y you are giving more weightage to the third bus, because obviously its probability is high, because you are going to pick up a student, most likely going to pick up a student who is from who is from bus 3, whereas driver There are nothing, there are 4 drivers, all are equally likely. So even if you compute it, it will change. So this will become 3 by 4, right, this will become 3 by 4, this will become 1 by 4, and this will become 75 by 200, right, sorry, 75 by 200, this will be some number, if this thing. So if it is 100, if I make it to 100, it will be even clear, but you will know that the probability value of the bus 3 will be much higher compared to bus 2, okay, clear, questions? No, this is what I would expect. It is not as difficult as you think if you start applying. If you do not apply your mind, you will never get the answer.